All right. So, according to this, a baseball player or a baseball on the moon and an identical baseball on Earth are thrown vertically up in the air with the same initial velocity of 10 meters per second. So let's underline that. What is the different maximum height the ball reaches compared to on Earth? Well, this is interesting because we were talking about force and energy and stuff, and I said there's a formula, and that formula is V squared is equal to V naught squared. The final velocity squared is equal to the initial velocity plus 2 times the acceleration times the displacement. And remember on our notes from the other day, we solved that for acceleration, and that's how we calculated kinetic energy, right? So now there's two ways you could do this problem. You could do this problem using this formula, and I'm going to do it. We're going to do them both ways so you guys can see. One, we could do kinematics, which is Newton's laws on motion and the equations associated with those. And the other way is we could use energy, conservation of energy. The interesting thing about this is that whatever the height is on Earth, it's probably going to be about 1/6 that on the moon. Okay? So let's do Earth. So I'm trying to think what's the best way to do this. Let me do Earth in blue. All right, so for Earth, what I'm really interested in is solving for X. So because they want to know how high up it'll go. And so I'm going to rewrite it just slightly and say 2 times Y, because we want to go in the Y direction, right? We're thinking to ourselves that this is a positive Y direction, right, going up. And so what is the initial velocity of the ball? I know that it is 10 meters per second at the very height of the ball. So I throw the ball up in the air, right? At the very height of the ball, at the maximum height of the ball, right there, what is the velocity? Well, the velocity is equal to 0 at the maximum height. When the ball is down here, we know that the initial velocity is 10 meters per second. And we know that the acceleration due to gravity is equal to 9.8 meters per second in the negative direction. All right. So I got 0 here. Okay. I've got 10 squared here plus 2 times negative 9.8, right, times Y. Is that good so far? So then in the next line, I've got 0 is equal to 10 plus, what's 9.8 times 2? I think it's 16.9. Let's see. No, it's 19.6. So we'll say 9.8 times 2. Yeah, it's negative 19.6. So this ends up becoming negative 19.6 times Y. So then the next thing I do is I subtract 100 from both sides. I get negative 100 is equal to 19.6 Y. Divide both sides by negative 19.6. The negatives will cancel out. I'm going to have to pull my calculator back up. $100 divided by 19.6. It's about 5.1, right? So we'll just make that 5.1. So that's the height on Earth. So now for the moon, I guess I'll do like a gray color. No, it's got to be a little darker. Okay. So now I'm going to do the exact same thing for the moon. I'm going to say v squared is equal to v naught squared plus 2ay. Same thing here. When the ball is at the top, this is my baseball, v is equal to 0 meters per second. At the bottom, v naught is equal to 10 meters per second. So I've got 0 here is equal to 10 squared plus 2 times the acceleration due to gravity. Now here is interesting. This is 9.8, but it's 1/6. So we've got to say 9.8. Move my face over here. I've got to say 9.8 divided by 6. So it ends up becoming this 1.63 repeating number. So my acceleration due to gravity on the moon is actually just 1.63 meters per second squared. So that's going to be 1.63 times y. I get 100. Oh, but this is negative still. It's still in the negative direction, so we still got to have our negative sign. So that 1.63, we got to multiply that by 2. And we get 3.26 repeating. I'm just going to say 3.27. Oh, that is not a good 3. Times y. On the next line, I'm going to subtract 100 from both sides. I get 100 is equal to negative 3.27 times y. We divide both sides by negative 3.27. Remember, when you take a negative and divide it by a negative, it becomes a positive. So I got to take my 100 and divide that by 3.27 now. And I get about 30.6. This is technically, I don't know. You guys know that this is a lowercase e, right, for Earth. And so if you do the math on it, the height is actually 1/6. But what they want to know is what is the difference between the two. So the final answer then that we need to come up with is finding the difference. So you would say the difference is 30.6 minus 5.110 meters, which is equal to 25. They said 25.5 meters. Now that was a lot of math, a lot of algebra to do that. And I'm not going to do the whole problem, but we could do the same thing with the conservation of energy. In other words, this initial velocity it gives the ball a kinetic energy at the beginning, and that would be equal to the full potential at the top. So what you could do is and I'll write this in a different color so we're not confused. Well, let's do green. I haven't done green in a while. So what we could have done for that exact same problem is figured out the kinetic energy, and that would be at the beginning, and that would be equal to the potential energy at the end. All right? So this would be the kinetic energy, and this would be the potential energy. So the kinetic energy would be 1/2 times the mass of the baseball times the velocity squared should be equal to right? We'll do Earth first, M, G, H. And what we would want to do is solve for H. Well, the first thing that I'm going to have to do is get rid of this line I just wrote down. Is if I take this and divide it by the mass, I get 1/2 times the velocity squared is equal to G times H. So then the initial velocity, this is technically the initial velocity, would be 1/2 times 10 squared, which is equal to 9.8 times H. So then we have to do the exponents first. So this becomes 100. What's 1/2 of 100? 50. So this would be 50 is equal to 9.8, right? Then I would divide by 9.8 on both sides. Guess what that is? If I say 50 divided by 9.8, it's 5.1. So we did that, and I don't know if it's less steps or more steps, but that's the same thing that we got by doing all this math over here. So that's two different ways to get the same answer. So we got 5.10 for the height on Earth. That's what we got when we did the conservation. And you do the same thing with the acceleration due to gravity of the moon, and you get the same answer. Sometimes it's easier to do the energy. Okay? Any questions? All right.